In this paper, we present MoGlow, a new general method for controlled motion synthesis. Our method is especially suited for tasks where the control signal is weak and the motion, therefore, is ambiguous. In these scenarios, conventional deterministic methods tend to collapse on the mean pose. Our method builds on a technique known as normalising flows, especially the recent work on GLOW from OpenAI. This model is probabilistic and can be trained using exact maximum likelihood. Our contributions include extending GLOW from the image domain to generating arbitrary motion, adding control by conditioning the output distribution X on a given input signal C, and a new autoregressive architecture enabling zero latency interactive control. The method is completely general and should work for any type of motion and input. In this work, we use human locomotion as our running example, taking body position and heading as control inputs. The task is then to animate a convincing series of body poses along a user-specified path through space. Control over the output is achieved by modifying the affine coupling layer from GLOW to condition that transformation on an external control signal. Novel motion is generated by sampling from the conditional motion distribution. This means that our method generates different motions every time, yielding a rich natural variation of movements. These two videos were generated from the same control signal. Notice how pace and stride differ between the two. MoGlow is a novel autoregressive architecture that further extends our controllable GLOW model for zero latency control in interactive scenarios. Conditioning information in MoGlow is shown in red. It consists of the current control input, together with the control signal from recent time steps, and recently generated poses from the motion sequence. A recurrent neural network allows long-term memory beyond the most recent time steps. Without recurrency, the generated motion is unstable and unrealistic. Long-term memory improves the consistency of the output. We also introduce a per-frame dropout scheme to prevent bias from past poses to override the control. Without this dropout, the motion is internally consistent but does not match the control. Introducing dropout makes the generated motion consistent with the control. Our dropout scheme also remedies issues with exposure bias seen in many autoregressive models, which tend to diverge from natural behavior when generating long output sequences. In these examples, we initialize the system with a static mean pose. Note how quickly our model recovers and starts to produce naturalistic motion. Here are some examples from the methods presented in our paper. A link to our manuscript on archive can be found in the video description.